Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. So if you're not familiar with the podcast, we are trying to gather the view from the scientific community, mainly here in the UK, regarding the challenges and opportunities associated to exascale computing with applications to turbulent flow, but not only, we are trying to gather the view from as many people as possible. So this podcast is part of the ExCALIBUR initiative, which is a big 5-year project here in the UK, dedicated to redesigning the software landscape with the view to use exascale computers in a few years' time. It's also part of the UK Turbulence Consortium as well, and you will find all the links for the podcast on the UK Turbulence Consortium website. So today we have a guest from EPCC, which is the Edinburgh Parallel Computing Centre at the University of Edinburgh. We have Nick Brown. Nick Brown is a research fellow. And I looked at his website today, and I think I found a very nice sentence to summarize his research and software development activities. It's to enable some of the most powerful machines in the world to most effectively provide scientific insights. So that I think that's a spot-on description. So good afternoon, Nick.
Hi. Hello, everyone.
Thank you very much for joining us today. So I'm going to start by asking my usual question. So for those who don't know you, or maybe not just know your name, so can you tell us a little bit more about yourself, where you are from, what you have studied, and how did you end up in Edinburgh at EPCC?
Yeah, I mean, I guess like most people, sort of fell in a little bit by mistake or good or bad fortune, depending on what your viewpoint is. In terms of I'm a computer scientist, and when I finished my first degree, there wasn't really any interesting jobs, or I thought was interesting anyway. So I did a PhD, and that was in programming language design and compilers. But it was I was a bodger rather than a squiggler. So I was very much applied to parallel programming. So sort of got into HPC from that perspective. I developed a parallel programming language and a compiler, and then ported Gadget 2 into my language. So it sort of got me into seeing the different bits and pieces and how people write code and MPI and OpenMP and the different technologies. And then once I'd done that, I actually went into industry for a couple of years. I worked down in the West Country for BAE Systems, and that was fine, but it didn't strike me that it was the sort of role that I could continue to get more and more technical with. And I wasn't necessarily working on really super cool challenges. It was what the business was telling me to do rather than what was maybe more interesting widely out there. So that's what motivated me to go back into academia, and I joined EPCC about 10 years ago, and haven't looked back since, so to speak.
Great. May I ask you, how did you become interested in computer science and, high performance computing? When that switch happened?
Yeah, I mean, I guess I've always been interested in computing. My grandfather had a BBC Micro. Many of you will probably remember that. Remember those computers in the UK, and that's sort of what got me into programming and doing that. And then at university, I found I just enjoyed doing it, and I enjoyed hacking around with stuff basically. And high performance computing struck me as one of those fields which is really exciting, because there's lots and lots of technical challenges for us to solve, and lots of technical challenges for us to solve in a sort of a programming style way. So I think that's what really attracts me to it, this idea of we have a clear vision of where we want to go towards exascale and why we want to get there, but actually there's a lot of baby steps that need to be taken and lots of challenges to do that. So that just sort of strikes me as being really cool and really interesting, picking some of these off and having this higher objective, if you like.
Great. So you say you've been working at EPCC for about 10 years or so. So what do you like about working at EPCC? What's the best thing about your current position?
Well, I think to some extent it really goes back to what I was just saying in terms of being able to be a part of these challenges. And what's really nice is to be able to pick your bit of it. Coming from a programming languages, compilers background, I tend to view things through that lens, challenges through that lens, and the solution will likely be seen from that perspective. But I like to be able to drive my research interest and what I think is interesting to do based upon HPC. And it's almost that wider impact that you can quite easily connect to, because we've got all these users, because we've got this desire from the scientists and engineers to run their codes faster, more complicated systems, etc., etc. And of course, EPCC, it's one of the world leading centers for HPC. So it gives us a lot of opportunities to be doing this and be involved in all the cool stuff that's going on.
Great, thank you. So let's talk a little bit about the ExCALIBUR project. So as I said in my introduction, this is a big 5-year initiative here in the UK, where we are going to look at redesigning the software ecosystem so that we are ready for the transition to exascale. So I know you're involved in a project called Efficient Cross-Domain DSL Development for Exascale. So can you tell us a little bit more about this project and what you are going to do within this project?
Yeah, absolutely. I mean, this is all about domain-specific languages, and a lot of people might disagree with me on this point, but I must admit, when domain-specific languages started to be talked about and started to be discussed, I was somewhat skeptical on them for 2 reasons. And the first reason is their acceptance by the community. I mentioned at the start, when I did my PhD, I developed a parallel programming language. I was very naive at the time. I thought, this is wonderful. Everybody's going to pick it up and use it. And of course, nobody did, because there's so much more beyond just a great technical solution to getting these things picked up. And I think with domain-specific languages, this is something that's actually, they've done very well in the community by moving them more onto the abstraction level. So in encapsulating these things in like Fortran or Python, and there's some great success stories there. But the other limitation, and the limitation I think is still around, is the fact that if you go with one domain-specific language or domain-specific abstraction technology, often the technology stack is very siloed. It's there and you go with another one, and it's there, and you go another one, it's there. And the challenge, of course, with that is if I buy into one technology, well, how do I know it's still going to be supported in 5 or 10 years' time? How do I know it's going to be on Archer 3 or whatever we call it? Yeah. So therefore, what we're doing in XDSL is looking at developing a common unified compilation stack, or at least technologies that enable people to build their domain-specific languages or domain-specific abstractions as a thin veneer on top of all this existing work that is well supported and ubiquitous out there. And what we're building this on, I would say the secret sauce, but it's all open source. So maybe the magic sauce is a better description, is we're building this on MLIR, so multi-level intermediate representation, and LLVM. And these are really popular technologies out there in the wider world. MLVR's only been around for a few years, but has massive industrial buy-in, and it enables you to lower your abstractions in a structured way to then very easily target different architectures and target different uses of your higher level code. So that's a very high level view of what we're doing. And I suppose the other comment related to this is our main focus currently are 2 domain-specific languages. So this is DeVito from Imperial and Cyclone from STFC, 2 fantastic technologies in their own right, but then using these to drive that stack. But also we're super duper keen for DSL owners to get involved and connect in with the technology and build on top of that. And we'd love to chat with you if you're one of those people.
Great, thank you very much. And so part of this, to all those ExCALIBUR projects, there is a role, is knowledge exchange coordinator that people are very keen in. And I know you are the knowledge exchange coordinator for this project. So can you tell us a little bit more about this role and, well, what does it consist in? Yeah, what do you do with that?
Yeah, I mean, I think it's a great aspect of ExCALIBUR to have brought this role in and have put this spotlight on actually how do we disseminate and exploit what we're doing as part of these projects. What I am very keen on with our XDSL project is to try and be the conduit between the HPC community and the compilers community, to try and connect these communities a bit closer and enable these domain-specific languages to become more ubiquitous. So whilst we've had a lot of conversations that whilst we are all about this sort of lower level stack in the project, actually more widely our ambition is to try and promote the adoption of DSLs within HPSC and writing HPC codes. So we've got some really cool plans. We actually had a BOF at Supercomputing 21, yeah, I've got the year right, in St. Louis stroke virtual. And that was really fascinating just to have that initial conversation around this is where we are, this is what we think as a community, how can we challenge ourselves? And with the contacts we've made and the ideas that we brainstormed and come up with, we've now started to look at building this. And we're really keen to be outward facing and to be having these discussions with people, the wider community. Already we've made some great contacts, but if, again, you're one of these people who thinks this is interesting, maybe has a technology you think could be useful as part of that picture or could tie in here, please get in touch, because it'd be great to have this conversation with you and grow this as a community thing.
Great. Thank you very much, Nick. That's a very nice description of your ExCALIBUR project. I have I'm following you obviously on Twitter, and I've seen you have been part of the urgent HPC workshops. And I was wondering if you can tell us a little bit more about that, because maybe people don't know what this initiatives is. So it would be good to hear a little bit about it.
I suppose I would say, I've got to be careful with my language here. I suppose I would say the timing was somewhat serendipitous, but what I'm really referring to is the pandemic. So there's nothing serendipitous about that. But I'll explain why I say that. In terms of, this has been driven by a European project that's actually just coming to an end called Bestec. And through that, I was very keen to look at this idea of running urgent workloads on HPC machines, but at real time. So you imagine you've got your forest fire burning. Well, the urgent responders can then run their workloads on the HPC machine and get feedback from it and then figure out how best to extinguish that fire.
Yes.
And so that is what motivated the workshop series, because there's a whole load of things we need to do on a policy and technical level in order to address this. The reason I was talking about the timing is we started this off at SC19. So this was before the pandemic, talking about urgent workloads. It was fine. We got some really interesting discussions, great keynote talk about forest fires. But actually what completely shifted the focus here, I think, in our subsequent two workshops at SC, the year later and the year after that, was obviously COVID. Yes. Because suddenly the idea of urgency, diseases, how can HPC help here? Well, it was much more in our minds and there was much more work going on here. So suddenly it was actually much easier to find keynote speakers. It was much easier to get people submitting things and get people interested in this because of the wider context. So to some extent, a fascinating view of how it also has grown from my perspective, seeing all these other things that have happened externally to that. But that's the idea, to try and have this conversation, to try and increase the benefit we're getting from our HPC machines to tackle some of these scenarios we face nowadays, emergencies and diseases. And
these workshops are going to continue, I guess?
Yes, absolutely. I mean, a plug actually. We've got a workshop with the interactive HPC guys. It's an interactive HPC workshop at ISC and that I'm also involved in. But these topics are very connected and very linked. So if people are interested in that, a couple of months, the paper deadline is in March. But yeah, absolutely. We're now looking at this as a route to then continue the workshops and continue the conversations, because it really does seem like this is something worthwhile to do. And as I say, it's grown and grown and grown from one year to the next. So it would be great to see if we can continue that and continue to see where we can take all these things.
Great, thank you very much. Can you tell us a little bit more about your involvement in the XLRAT project? So yeah, once again, some of the people listening to the podcast might not be familiar with this project. So can you tell us a little bit more about it and what was your involvement in it?
Yeah, so XLRAT is one of the European Centres of Excellence.
Yes.
And it's all about making some of the key European engineering codes exascale ready. So looking at the supercomputers we're going to have in the next, I don't know, 5 to 10 years, hopefully a bit less time, and taking the codes as they are now and making them able to exploit those machines and understand what that looks like in a bit more detail. It's a big centre of excellence, across a whole bunch of different centres in Europe. My focus on the project has been actually quite narrow. It's been looking at the role of next generation technologies for accelerating our codes. So obviously, if we think back to 15 years ago now, GPUs were very novel for accelerating codes, and we've had massive benefits from going with that. So the question is, well, in the exascale era, of course, GPUs are going to be a major part of that, but what other technologies are there out there on the hardware side that we might be able to use? And one of the key things I've been looking at are field programmable gate arrays, FPGAs. And this is really nice because it enables you to tailor the execution of the electronics to your code. And you might say, well, why on earth would you want to do that? But the reason for that is because then we can get rid of this black box microarchitecture. So you can utterly tune the electronics, the logic, the memory to suit your application. And what we found is potentially you might have a kernel in your code that's really memory bound, or maybe it's bound by other microarchitecture factors. Well, having that additional flexibility then enables us to get rid of those overheads and address them. Of course, the devil's in the detail. It's far less mature for running HPC workloads. The vendors have done some wonderful work in the past couple of years, like Xilinx, around their technologies, the hardware, and also the programming of these. But I think now it's our question as software engineers to think, right, algorithmically, how do we write these? What kernels do we focus on? And what are we ultimately going to get out of the technology? And so I've been picking a number of our applications and focusing in on that and doing these experiments, which I found fascinating. It's been really good fun for me.
Great. I have a slightly controversial question, a follow-up of what you're saying. Would you say that FPGA, it lost a little bit of traction recently? I mean, it seems that we are talking a little bit less about it, and we are talking more about the new generation of GPUs and so on, or do you say there's still a chance to see this technology at large scale?
I think that's a great question. I suppose it really depends on what your perspective of it is. It's maybe a little bit more difficult for me to answer that because I'm really close into it. So yes. I see lots and lots on the FPGA side as I'm working with it. But what I would say is there's some really exciting FPGA technologies coming out. For instance, Xilinx have what they call their Versal, and this combines the fabric with a whole load of, they call them AI engines, but basically they're vectorization engines. And you can have up to 400 of these, which potentially is going to give some great performance. Now, currently, there are some experimental engineering samples out there, and they're coming out more widely, I think, later this year. So I think what we're going to see is really, as you say, one type of hardware gets a benefit, and then people start using that, and then another type of hardware gets benefit, and people start using that. So I think these things will hopefully progress sort of side by side.
Yes.
But of course, what you have to do is you have to pick your battles. And if you just say, well, I've got this kernel, I'm going to accelerate it on X technology, maybe it's not going to work. You need to have a good reason why you want to put it on that hardware and that hardware. We really understand that for GPUs. Maybe for FPGAs, we don't fully have a handle on that. And again, we need to build up this knowledge of a community, exactly how to leverage these and exploit them. So that's maybe how I'd answer that in a roundabout way.
Yeah, that's great to have your view on this. Sorry, I've completely unrelated questions now. I know you have been working with the Met-Office near cloud model. So can you tell us a little bit more about your activities with Monk?
Yeah, I mean, this project sort of makes me smile in terms of, I mentioned at the start, I'm a computer scientist and a bit of a bodger with compilers and programming languages. And I think often with these things, you do some great research on the computer science side, you make it available on GitHub, and then maybe not that many people use it. Now, what's been fantastic with Monk, with this Met-Office work, is it's been the opposite. We did this about 8 years ago, and there's actually quite a nice community. The Met-Office use this as their main high-resolution atmospheric model, as well as the UK weather community. So it's, I suppose, a completely different view on writing software and writing HPC applications from some of the other things I've done, which were much more on the research side. And the idea of that was the Met-Office had a model from the 1980s, 1990s that was getting quite old. It wasn't designed for modern supercomputers, wasn't designed with modern software engineering techniques. So we did a rewrite of it to enable it to then run on latest generation architectures like Archer 2 on hundreds of thousands of cores, and with modern software engineering techniques to then improve the code generally. We worked on this about 8 years ago, but it's still ongoing. People are still using it a lot. We've actually got an active ECSE project at this moment, looking at doing optimization for Archer 2 to be able to push it to the next level, which those 750,000 cores on Archer 2 enable us to do compared with any previous generation supercomputer we've had in the UK. So it's something that I actually view as one of the jewels in my career of EPCC, if you like, something I'm really proud of, because people do use it and people do care about it. And, it's quite cool to produce something that you can then say is used by people like the Met Office for these different things. And I'd also say, going back to our ExCALIBUR domain-specific languages project, that's actually one of the use cases, one of the application cases that we're looking at here. We're looking at building these domain-specific languages on top of our ecosystem, but then we evaluate that with a whole load of applications. And one of them is this Monk model to really see the difference in the impact it makes, portability between different hardware, different architectures, program productivity, etc.
Great. I have one last question before my philosophical question about exascale computing. Can you tell what is EPython? I know this is something you have been working on, and I'm very curious to learn more about it.
Yeah, sure. I mean, again, I suppose it's an illustration more widely of how having a fun little idea and just exploring it a bit can take you on very unexpected directions. I don't know if you remember, some of the viewers might remember, about 10 years ago, a little bit less, there was an architecture called the Epiphany that was developed by a company called Adaptiva. And at the time, this had 16 cores. They also had a 64-core version of this, and they taped out a 1024-core version. And it was really cheap. And the idea was for less than $100, a supercomputer on the desk. The downside was it was really difficult to program. And I mentioned with my background, I tend to view everything through the lens of programming languages and compilers. So I thought, well, why don't I do a port of Python to it? The limitation is you only had 32 kilobytes of memory per core. So I implemented the world's smallest Python compiler called EPython, no, Python interpreter initially, 24 kilobytes. It was fine, but as an interpreter, it went about 100 times slower than what you would have if you wrote the code natively. However, what I then did is had a very intelligent PhD student, luckily, who took it and did two things. The first thing he did was write a compiler around it, where what we do is we compile against a virtual machine, but fold that virtual machine in during compilation. And this gets us down from about 24 kilobytes to about 6 or 8 kilobytes. But also we can be really clever by swapping code in and out. And if I was conservative, it gives us about 90% the performance of natively written code in C. But if we are a bit lazy, like most people I always see, we can often beat it. But then the other side of this is, unfortunately, Adaptiva didn't continue, the Epiphany didn't continue. So instead, we focused on moving this to RISC-V. And that got us into RISC-V. This is a new, not so new, open source architecture where people can build a whole bunch of open source CPUs around the instruction set. And it really opened up exploring this architecture for us, which I think is hugely exciting in itself. So that's, I suppose, a brief view of what EPython is.
Excellent. Are you still working on it, or? Yeah,
we are. I mean, actually, at the moment, there's an active project that's going on. It's called Vipera. We've renamed it. My PhD student, he'd contributed enough to it where I gave him, well, I said to him, it's fine, if you want to rename it, we can move it from EPython. I don't think he ever really liked the name, to a name he preferred. So yes, we've got a project on it at the moment that we're working on, absolutely raising the technology readiness level. And people can download it and play with this. And yeah.
Excellent. Right, I have a few more questions. As I said, they're more philosophical. So when you are working at EPCC for, you have been working for 10 years, you are seeing on a daily basis lots of software and so on and so on. So very simple question, difficult answer, but do you think we are ready for the transition to exascale computing?
It's a good question. I do think programs like ExCALIBUR are absolutely fabulous for focusing in as a community and picking off the challenges towards xScale and getting us to work on these. I suppose I would have to say, as it stands right at the start of 2022, probably not, but that's maybe because ExCALIBUR runs until 2024, 2025.
Yep.
So, you know, maybe by the end of that. But I think more widely, look, there's some really exciting hardware obviously coming online across the world. I think there's some great work being done more at the research council level. There's some interesting talks at Computing Insight UK about that. So it looks, I think, like a really exciting future for exascale for the UK. But I do think there'll be a lot of work from the perspective of programmers to make sure simulation codes can actually take advantage of this. If we were to give an xScale machine to a simulation application owner, you know, how many cores are they actually going to be able to run over? So I do think there's quite a bit of work needed from that perspective, and hence programs like ExCALIBUR and other things like ECP in the US. Great,
thank you. And so you have been working with various hardware technologies. The story about EPython is a good example. Overall, I mean, are you happy with the hardware and the high performance computing tools that you are given to play with? Or if there is something that you could change, what would that be?
So I think on the hardware, I don't know, a lot of people would disagree with me on this. I sort of expect things to get a lot more heterogeneous, and I might be completely wrong. And I'm not just talking about where we're going to have this accelerator like FPGAs and pull them in, although I think that absolutely will happen. But I'm also talking about things like RISC-V. What that suddenly opens up is you can have all sorts of weird and wonderful accelerators that you combine with these things, because it's all open source and people produce these things. The designs are online. You can program effectively an FPGA with these things or build them in hardware. So actually, I think we might start to see on the hardware side a lot more specialization to applications, because it just opens up being able to do all these different bits and pieces. And I also think, and again, I think maybe this is a safer thing to say, that we need to view this much more holistically. So it's not just a hardware, it's hardware and all the libraries and how we program these things and that whole stack in terms of enabling this. So we need to view this as a collection, I think, of technologies, making it so application developers have no excuse not to adopt them, rather than just let me give you some hardware and you've got to use it. So I suppose one thing in HPC I could change would be maybe, you know, some of the reticence around that. Obviously, we've been around for a very long time, which is great. We have some fabulous codes out there that have been around for a long time and have been very well tested. But what it does mean, of course, compared with communities, maybe like some of the data communities, which are much newer, they obviously are much more accepting of completely new frameworks, completely new technologies, fast to fail, and all of that, where maybe in HPC we're a little bit more risk averse. I know some people might disagree with me on that, but maybe that's my view on what I might be able to change for adoption of some of these things.
Great, thank you. And I have one last question. So obviously now the hot topic is exascale computing and exascale computers, but I'd like to have your view of, I mean, what are we going to work on or work with in maybe 20, 30, 40 years? What do you think that we are going to see a revolution in terms of hardware? So I'm thinking of quantum computers, or do you think in 25 years we'll still be working with some sort of GPUs, CPUs, and with very similar Fortran, MPI, or what do you think about the very long term in terms of high performance computing?
Yeah, I think it's a great question. It's quite a difficult question to answer.
Obviously it is, yes.
On the one hand, I think we often over exaggerate what the future will deliver in terms of single massive impacts. And what I really mean by that is, if you look back 25 years, maybe pushing to 30 years, that's when MPI was starting to be standardized. So we've had that for a long time. And so the fundamental, and Fortran even longer. So these technologies that we're using and we're relying on now, actually they've been around for a long time, but there's been so many other disruptors out there with HPC, like GPUs, for instance, the power of the machines, and all these different dimensions that come in there as well. I don't know, I suppose I would put my money on, firstly, domain-specific languages, because I think as machines get bigger, more complicated, more heterogeneous, we just can't program them manually as we're doing. We just don't have the brain power. So we need more help from the compiler. And I think improved compilation support and some of the work around MLIR and other intermediate representations, I think will help there as well. And then also on the hardware side, as I mentioned before, I think things will get a lot more diverse personally. Maybe that's a somewhat contentious point, but I do think there'll be more specialization for applications. Just because I think scientists, we're continually making the case for this more powerful machines. We'll reach XScale and then we'll have the one beyond it. I'm not sure what 10 to the 21 is, for instance, but we'll continue to be doing that because scientists are continually pushing us. And so I think that will hopefully lead to further developments of these things. It does seem to some extent that we focus so long now on exascale, exascale. We sort of need to remember that exascale isn't the end. There's then going to be a whole bunch of things beyond that, because we're never going to keep these people happy based on what we want out of our simulation codes. And clearly with all the success stories out there, HPC just is so important.
Great. Thank you very much, Nick, for taking the time to chat with us and for your inputs about high performance computing, exascale and programming and DSL and so on and so on. It's very nice talking to you. So thank you very much.
Well, thanks very much for having me, and thanks for listening.
So thank you very much, everyone, for listening to this podcast. As usual, if you Google UK Turbulence, you will find the link for the UK Turbulence Consortium, where there is a tab for all the podcasts and all the links. And I will be putting all the information regarding Nick podcast on Twitter, and I will share Nick's webpage. So if you are interested in Nick's research, you can discover more about him. If you want to contact him, of course, feel free to do so. So thank you very much for listening to this podcast, and hopefully I will see you soon for a new episode. Thank you.